All chemical bonds are formed as a result of sharing electrons between two or more atoms. In this video, we will explore the similarities and differences between ionic bonds and covalent bonds. Consider what happens when two hydrogen atoms approach each other. At large separations, more than about 150 picometers, the attractive potential energy is very small. However, when the electron clouds begin to overlap, around 100 picometers, the potential energy decreases. This energy difference will eventually be released as heat, and a bond between the two atoms begins to form. At a separation of 74 picometers, the potential energy reaches a minimum, and the bond is formed. Notice that it would require more than 400 kilojoules per mole of energy in order to separate the two atoms again. So this bond is very strong. If we tried to force the two atoms closer together, the unfavorable Coulomb repulsions between the two electrons and between the two protons overcomes the favorable overlap, and the energy starts to increase rapidly. Therefore, hydrogen molecules maintain an optimum bond length of 74 picometers. It's important to remember that all chemical bonds form as a result of lowering the potential energy of wave functions or orbitals that are occupied by electrons that are shared between two or more atoms. The details of this sharing determine the sizes and shapes of molecules, the strengths of bonds, and the physical and chemical properties of the compounds and materials. Electrons are not always shared equally between atoms. Electronegativity measures the tendency of an atom to attract a shared pair of electrons in a chemical bond. The most electronegative elements are fluorine and oxygen, and the least electronegative elements are the alkali metals, like lithium. Helium doesn't have a measured electronegativity because it doesn't form chemical bonds with any other element. The electrons in a bond between two identical atoms, like nitrogen, are shared equally because the atoms have identical electronegativity. So we say they form a pure covalent bond. If the negativities of the atoms are somewhat different, as in carbon monoxide, the sharing is unequal, and the oxygen end of the molecule acquires a partial negative charge, while the carbon end of the molecule becomes partially positive. This is called a polar covalent bond. Finally, if the difference in electronegativities is large, like between lithium and fluorine, the electron transfer is essentially complete, and the two atoms form an ionic bond. Covalently bonded compounds usually exist as intact molecules. They may contain as few as two atoms, like nitrogen or oxygen, or hundreds of atoms, like proteins. They may exist as solids, liquids, or gases, depending on the temperature and the strength of attractive intermolecular forces between the molecules. Covalent compounds usually dissolve in water as intact neutral molecules. An important exception is acids and bases, which may partially dissolve as ions by transferring a proton to water or by taking a proton from water. There are several different common ways of denoting the bond connectivity in covalent compounds, including stick figures, space-filling models, and ball and stick models. The strengths of individual chemical bonds vary, but typically lie in a range of about 200 to 400 kilojoules per mole. Ionic compounds, on the other hand, are almost always present as salt crystals, in which the attractive interactions between positive and negative ions are not between distinct ion pairs, but are instead distributed over an extended volume of the crystal lattice. Lattice energies vary widely, but for many crystals lie in the range 1,000 to 3,000 kilojoules per mole by formula unit. At high temperatures, many salts will form an ionic liquid, or molten salt, that can be useful as an environmentally friendly solvent or as a coolant for high-temperature environments like nuclear reactors. One defining characteristic of ionic compounds is that when they dissolve in water, they form separated positive and negative ions. Ionic compounds usually adopt one of a few different crystal structures to optimize the attractive interactions between positive and negative ions, depending on their relative sizes. However, we shall see that the structures of covalently bonded molecules are much more complicated because of the many ways that the atoms can be connected to each other. These structures may be small or large, rigid or floppy, volatile or involatile, reactive or inert. This is all part of what makes chemistry so interesting and challenging.